Okay, so we've talked about the qualitative aspects, no math, of solutions. Now I want to talk about the quantitative part of this. So basically it comes down to this. How do you measure concentration? Now there's a number of ways to do it. When you're cooking, usually you're talking about um, ounces of dry stuff and so many, ounces of liquid. But in chemistry, we don't do that. We get to use good old moles. So there's something called molarity. And when it applies to solutions, the definition of molarity is moles solute to liters solution. Solution includes solvent plus solute. So it's moles per liter, and it's abbreviated capital M. So for your Friday lab people, remember the hydrochloric acid had a 3M on it? The M was the molarity. That stood for 3 moles per liter of that acid. And you Saturday people will soon see that. There's another term used in concentration, and it's a lowercase italicized m, and it's called molality. There's molarity, molality. And that's moles per solute per kilogram of solvent. Now, it's real important to distinguish between these two. This solution includes the volume of the solute. This does not include anything about the solute. That's strictly solvent. Now, you're going to use this a fair amount in your next chemistry class, molality, but not in here. We're going to be using moles per liter. It's going to be enough, trust me, moles per liter. And molality comes into play when you have to calculate something called colligative properties. Colligative property, for example, is when you add something to your water in your radiator. It's called antifreeze. What it does, it lowers the freezing point, raises the boiling point. You throw salt on your sidewalk during frosts. It lowers the temperature at which the ice will melt. Okay, those are called colligative properties, and you have to use molality to calculate all that. Okay, so moles per liter. So let's look at a simple problem. Okay, and from now on, we're going to be, the solvent is always going to be water. Okay, so definition of molarity. Molarity then is moles per liter, and that's per 1 liter, per 1 liter. Okay, well, we don't have moles, we have grams. So what do you have to do? We have to convert the grams to moles. So we're going to have 34.5 grams. Sodium is what? Is it 22.99? And chlorine is like 35, 45. Oh, yeah. Yes. Okay. So the numerator is moles, denominator is volume. Okay, so to do this little quickie, now you can do this two ways. The way I do it is I go 34.5 divided by 58.44 divided by 3.45, enter. Okay, you can also do it in two calculations. You can do the top calculation, write it down, or store it internally, then divide again. Or you can do it in one deal like I just did. So you have basically, you have two divisions. Remember I said when we have anything on the bottom, you hit the divide key. Well, this is on the bottom, the 58, and so is the 3.45. So you go 34.5, divide 58.44, divide 345, enter. So now I want you to, in your mind, interchange all the time the big M. I usually boldface it with an underline, and the moles per liter. Just all the time when you see those two, think of them together. Because next week's lab, you're going to be using that quite a bit. Okay. So does that make sense? Moles per liter. Okay, so let's do another one. Okay, so how many grams of sodium chloride are there in 3.45 molar? Let's see, let's rework. Let's see. 3.45 molar solution, 5.67 liters. Now this is a two-step process. Okay. So knowing again moles per liter. So we can rewrite this statement. Like that, right? Because capital M moles per liter. And we have 3.67. So where do we want to go with this? We need to get to grams. And one step we can get to moles. And if we know the moles, we can then go to grams. So it's a kind of, in your mind, think of it as a two-step problem. Okay. So how can we get moles out of this solution, this calculation? So the given is 345, right? What do we multiply that by to get moles? Well, Avogadro's number is going to say 6.02 times 10 to the 23rd molecules per mole. Moles will cancel, leaves us the molecules. If we wanted to know how many particles were in this, that's the way we do it. Okay, how can we just get plain old moles? That's for gases only. She said 22.4 liters per mole. That'd be gases. What do we multiply this by to get moles? Hmm? Well, we have liters here, right? What if we multiply the liters times moles per liter? What does it give us? Moles, because the liters cancel. No, that's just plain old, it's nothing. It's just liters. But the one, it's not correct to put the one underneath it, though. I mean, mathematically it'll work out, but there's not a reason to put a one there. It's just plain old how many liters of water you got. Okay, so let's do this calculation. 345 times 567. Okay, so that gives us okay, so it gives us 23 moles of 19 points. How did we get 23? Well, it helps to put the right numbers in. What? Yeah, 19.6 moles. That does not give us grams, though. So now we're going to go moles to grams. And it was 58.44. 114 grams, 3 sig figs. So you can do this in one step if you want. You can put this right here, one, not one step, but one line, or you can think of it as in two parts. Conceptually, I think it's easier if you think of it in two parts. But mathematically, you can do it. So if you want 345 for 1 liter times 6.70 liters times 58.44 grams per mole, the moles would cancel, liters would cancel, leaves you with grams.
Maybe 1,000. Yeah.
Oh, you mean I screwed up again? You know, this is kind of like a broken record, you know, or for you young people, no, not even a scratch CD, a uh, corrupted MP4 file. Yes, it'd be like that. To where? This up here? Okay, that problem is not related to this problem. And this one I want to know the molarity. I want to know the concentration, moles per liter. So first thing you do, you convert the grams to moles divided by the liters. Now I'll give you this guy here. Actually be an MP3 file, not an
Actually,
Oh, the vinyl, yeah. When I was in school, I had an Akai reel-to-reel tape recorder and what was the name of that? I had a record deck. It was a belt-driven one, so it was no vibrations at all. And I lived in Davis Mobile Estates, and my trailer was next to the tracks. So every time these heavy-duty trains would come by, my turntable would start to move like this and then crash because it would bottom out. So yeah, and what I would do, I would play my records once, and when I played them once, I would record it, and I'd listen to tape from then on because my records were stayed in really good shape. And yeah, when I was on Akai. Akai's still around, but they don't do reel-to-reel tape recorders anymore. Are they coming back too? Curiously. And I had giant speakers and big amp, and it was everyone.
I don't think it's like a tape, but like a tape player, tape player. I don't think that's
Vinyl is a pain. They scratch so easily, and depending on the quality of your system, it detects the scratches even more. So if you have a really crappy system, you pick them up with your hand, you know, everything instead of like. Are the vinyls expensive? 20 to 30. Of course, unless you're a DJ, you have to go. Then it doesn't matter if it's scratched or not. Okay, so that's what I wanted to cover today. Now, on Friday, we're going to get much more complicated than this. I'm going to take two solutions and dump them together to create the new concentration. So it reminds me of the two givens in a stoichiometry problem. How it adds complexity. Same with this. Two solutions, dumping them together. Two different solutions, different concentrations, dumping them together. What's the new concentration? So then we're going to get into acids and bases also. Okay, so the building was not open when I came today. It's supposed to be open from 10 to 6. And Oh, it is. Yeah, because when I got here, the guy must have been just behind me, the security guy. Oh, good. Okay. All right. Let me